And NumPy arrays, if you remember, something that's special about them is that all of their elements are contiguous in the computer's memory. And the only way for that to really be the case, for them to be contiguous and of equal size in terms of each data element taking the same amount of space, is that a NumPy array has to have elements that are all the same data type. That's a defining feature of them. So for Pandas data frames, or sorry, for a NumPy array, that's the defining feature of them. For a Pandas data frame, each column has elements that are all the same data type. But each column individually could have a different data type than the other columns. So you could have a column that's made up of strings. You could have a column that's made up of integers, and a column that's made up of floats. So they can have different data types associated with them, yeah.
Doesn't your data frame have a key, like a primary key, that keeps track of the, does it have a key input, like a primary key on itself?
Oh, a primary key? We'll get to indexes shortly. That's kind of what you're getting at, I think. So, in fact, we'll just get to it right now. But first I want to talk about the columns. This is the column names. If you wanted to access the names of all the columns in your data frame, you could call the df.columns. If you wanted to access the labels of each row, that is these guys in how it's visualized, you would call df.index. Now you see here that the index we get back for this particular data frame looks kind of funny. It says it's a range index starting at 0, ending at 1599 with a step 1. The reason for that is when we built this data frame, we didn't specify what we wanted to be the index for it. So Pandas defaulted to a start at 0 and go until you run out of integers, run out of rows index. And this is actually very small in memory. It doesn't have to store 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in memory. It just has to store that this index starts at 0 and ends here and has this step. It's kind of a compressed representation. So Pandas is already doing some nice things for us to be kind of memory conscious. That being said, it is possible to build your own index. And for this wine data set, you could imagine that if we had a column that was maybe the wine name, you know, like deep red or gentle fluoride, or I don't know, come up with whatever kind of cute name you want for each wine, you could actually use that as an index. You could use that as labels for your rows. It doesn't just have to be 0, 1, 2, 3, 4, 5. You could actually have strings as your labels. So for this example, I said we could use time as an index for this little example data frame. Turns out that you could even use something like strings as an index for a Pandas data frame. So there's a lot of flexibility with these things. And depending on the data set and what you want to do with it, different approaches may make different kinds of sense. Say again?
Could you like take on the columns and have that be the index if that had a name or label?
Yes, actually. So his question was, can we take one of these columns and make that the index? You usually want something that's going to be unique for each row, and I don't think there's any guarantee any of these are going to be unique, this particular data set.
Yeah, like a name or something you're talking about.
Yeah, usually want to go with something unique for an index, but that's not required either. So let's go ahead and do it. There's a method called setIndex, and that allows us, for example, to set, let's pick something. Let's pick the densities aren't terribly unique. Volatile acidity is not either. I don't think we're going to get anything that's terribly unique here. Let's go ahead with fixed acidity. And if you call that method, what you get is a data frame that looks kind of like the one we just were playing with. But instead of on the left having 0, 1, 2, 3, 4 as its index, it now has this fixed acidity index. quick show of hands, does the word primary key mean something to you? Raise your hand if yes. Okay, so at least half the class, I think, might have a sense for what this could be useful for. You could think of an index as a primary key on the table. It's a hopefully unique representative of each row. In this case, with what we've done here, it's definitely not. You can see 7.4 is represented many times. But typically, you'd want something you can grab onto that's unique for each row. Importantly, a lot of these methods of a data frame return a new data frame. So I just called this method setIndex. If I scroll down and I make a new cell and I call df, you'll see that where'd my index go? I thought I just set the index. That method creates a new data frame and then spits it out as the returned item from calling it. The original data frame is left intact. For a lot of methods, if you want to change the data frame in place, you would need to call, for example, setIndex. You would need to call that with this argument in place equals true, and that will actually edit your data frame in place, or at least do as much as it can to change the data structure in place. Any questions on that? It's a little bit of a subtle aside. Okay. Let's talk about how we can select things out. Just like with a NumPy array, we talked about slicing and selecting different elements out of a NumPy array with indexing. You can do a similar thing with pandas. So, say I wanted just the citric acid column. I could open square brackets, give the name of the column citric acid, and if I run that, that will select out that column and give it back to me. This is what's called a series object. There are two objects of primary importance in Pandas. There's a data frame, which is what we've been working with. It's the primary data structure in Pandas. There's also the series object. And a series object can be thought of as being a column of a data frame. In effect, you could think of a data frame as just a bunch of series objects tacked together with a common index used to index them. Here we've got a series object. It has the same index as the data frame we got it out of, and it only has a series of values. It's one-dimensional. I'm going to hold on to this. We're going to call this CA for citric acid. We'll explore some of the methods of a series, and we'll see how these actually kind of relate to the methods of a data frame. Just like a data frame, or just like a NumPy array, a series object has methods like mean, which would get you the mean value of all of the elements in the series. It has things like min, has methods like max. It also has standard deviation. So we're getting into some statistics, some descriptive statistics. It also has standard error of the mean, not to be confused with the standard deviation. We'll learn a little bit about how that differs from standard deviation, hopefully next week with our statistics lessons. We also have a method like describe, which will give you back a whole bunch of descriptive statistics as a series object. So this method describe, it's a method of a series. It actually returns a series that includes as its index a bunch of strings essentially and values as its values, or in this case, floating point numbers. You could directly access, for example, the standard deviation from that series if you wanted to. I did something kind of funny here, right? This gives me back a series object. It turns out that I can take a series object and I can select out values by their index label. So for example, if I wanted min, the value corresponding to min, I could do this. This is a case in which the index is made up of strings. So I mentioned earlier that for a wine data set, it would be kind of cool if it had an index that was the name of the various wines represented in the data set. We don't have that, but this is one of those cases where we have an index that's made up of strings. We could use that. Any questions on that? It's a bit strange, but it's kind of a defining feature of Pandas that allows you to work with labels. We didn't have to say, give me index 3, although I believe you could do that. That happens to be the third element of the series, happens to correspond to the label min. It's the same thing.
Does it automatically truncate the precision?
Say again?
Does it automatically truncate the precision?
The precision?
So,
Oh, I see what you mean. It's 0.0 instead of 0.00000. Because this is a floating 64, this is exactly 0.0, so it's able to kind of leave it off. How it's displayed here is kind of just an artifact of how it's displayed. I think the reasoning is that this number above has more precision, and it by default goes out to a certain point, so it displays all of these to the same precision. That's at least what I think is the explanation for that. Does that make sense? Okay. Let's go back to our data frame, df. There's some methods that are pretty useful, like head, which will give you the first 5 rows of the data frame. Likewise, there's tail, which will give you the last 5. If you don't want 5 and you want something like 10, you could feed in a number there and it'll give you the last 10 in the case of tail, or in the case of head, whatever number you specify. That's useful for getting a view of like, well, what does this data kind of look like, at least in the first few elements. If you want to access multiple columns at once, so we've so far grabbed something like citric acid, we get back a series. What if we want multiple columns? If instead of a single string or single column label, we feed in a list of column labels, like let's add chlorides in here, and then let's also put in density, then we could get a new data frame that features only those columns. We can also subselect on the rows. So far we grabbed one column or we grabbed many columns. What if we wanted to grab a bunch of rows? Well, we could grab individual rows by doing something like .loc df.loc, and then you open square brackets on that. This is a bit of a weird thing, so probably pay a little close attention to this. I'll explain a little bit more as we go. If I take .loc and I feed it a number like 1591, say this row right here, that label, then I will get back that single row as a series object. So notice that the index of that series is a bunch of strings. It happens to be the column labels corresponding to each value. This is actually a bit of a, there's a bit of a gotcha in here somewhere. Remember I said that series objects or data frame columns all have the same data type? If you call df.loc and grab a single index, you'll always get back a series object. But what if each of those columns had a different data type? What's going to happen is they're all going to get cast into the lowest common denominator, basically, data type. And what that usually ends up being is what's called object. So when you get back a series by doing a direct index like this, if you had, say, a string column in here, which we might do later, just add one just for fun to see the effect, the D type at the bottom here would be D type object, which means that the data frame kind of did a bit of a Hail Mary and said, well, I'll just represent pointers to things. It'll be a little bit less efficient, but basically each element of the underlying array will just be a bunch of pointers to the corresponding objects. It's not really that important for you to remember all of that right now, but it's something to keep in mind if you do this later and you're wondering why you get weird results, because everything got casted into something that otherwise it maybe wouldn't have been casted into. Like if you had a bunch of integer columns and some floating columns, now suddenly all of their values will be floats. And if you were depending on them being integers, then something will go wrong. Yes, the method to do this that doesn't change this is to not do a single index, but instead do something like this, which looks really weird. This is label-based indexing. It says, get me the rows corresponding to label 1591 up to and including 1591. This is where Pandas makes a little departure from the usual slicing rules. And it only does that departure for these label-based indexing. It's the one place where there's kind of in this course where there's a bit of a departure here. There's a good reason for why they chose to do it, but it sort of adds a little confusion. But this will select that as a row. So instead of getting back a series object, what we got back was a data frame that happens to just have a single row in it. And that maintains the individual D types of all of these columns. If you were to actually ask for the D types of this data frame, you'd see that they're preserved. That's kind of the safer way to do things. So that's an excellent question. Thank you. Any questions on that? Yeah.
What we talk about throughout this course, like how to handle, kind of in your example here, where you have data that has something like a string or missing data or some weird data type of blank spaces,
Mm-hmm.
and how to, because I've had instances where it converts it out of object, but I want it to be like a number that I can do math
Like
for the data types.
missing data or things like this, or? Yes, so let's do a quick side excursion. I'm going to go all the way back to the top of my notebook here, and I'm going to grab one of these data frames here where I created one with a missing value. Actually, I'm going to grab the top one, just this guy here. So if I make a data frame, I'm going to call it example df, and it looks like this. This guy has one missing value in it. And so I'm going to try to address your question, how to handle this thing. Well, it turns out a lot of methods on a data frame will automatically do kind of what you hope they would do with missing data. May not be what you always hope, but it makes sort of a sane choice. For example, if you were to ask for the mean of this data frame, there's a mean method. What you will get back is a series where the columns are indices, and you've obtained the mean of each of those columns. Now, if we look back at our original data frame, we see that the mean of D that it calculated is 7. What mean does is it will ignore missing values. So it'll automatically do some kind of handling there. But that doesn't look like it's answering your question.
Not quite.
Okay?
Like when I've imported like a CSV file, it'll be like in weather data, they usually have letters.
Gotcha. It's often the case that real data is messy, and you have to do a lot of cleanup beforehand. Something that we won't, unfortunately, have a whole lot of time for this course is data cleaning, but that's actually what you probably spend a lot of time on if you're working as sort of an industrial data scientist, is trying to get data in the form you want it in so you can actually do really productive work with it. And I've sometimes cracked open data sets in a text editor because like CSV files in Vim and started working on them a little bit because that was the easiest way to get to where I wanted to go. There are ways of doing a lot of this in Pandas, and often I'd prefer that because then you can at least rerun it all when you get a new crappy data set. I'll show you one quick way of at least handling missing values, things that Pandas flags as a missing value. So if I say exdf, there's a method called drop NA, and this would actually, the default behavior of this is it will drop any rows that have missing values in them. So say you're kind of like, well, I don't really want them in there. There's only a few of them in thousands of rows. I can get away with it. You might just drop them out. There's also, so in addition to drop NA, there's also I believe it's, what's the one? Fill NA, that's it. I was looking for it. It's not replace NA. It's not do something else with NA. It's fill NA. What fill NA allows you to do is to fill in missing values with something that maybe you're more capable of dealing with, or maybe whatever code you've written is better able to deal with. So maybe for you, filling NAs with -1s makes sense. Maybe that's some kind of indicator that this is not something I want, but it makes the rest of the code you've written that operates on it able to handle it. That's a quick way to deal with missing values. But what you're asking about is, if I have a data set that has all kinds of funny, awful characters in it, how could I handle that? The way that I would do it in general is to use exdf.apply. This allows you to apply a function along an axis of a data frame. And what that means is you could write a function that takes in each row and does some kind of processing to the elements. And like on an individual element basis within the row, and then spits out a new row that has the processed results. So for example, I'm going to write a quick function called add2, and it's going to take in a row, and what I'd like it to do is to say row, actually let's say this, fix my rows, fix rows. Say you have some really crappy rows and you need to do some stuff with it. I know that these rows have an element A in them, and I want it to set element A equal to row A divided by 3. Maybe I need to rescale everything to be like in units of 3. Maybe I need row B to just be left alone. I'll just do that for now. Could probably have just left it out entirely. And let's stop there. Let's return the row. If I now call exdf.apply, it's been a while since I've done this, so let's see if we get the result we're looking for. I think if I do axis 1, that will apply that function to each row. Notice that our resulting data frame has the values in column A rescaled. The values in column B were left alone, same with C and D with how I wrote this function. But if I needed to do something like set D equal to missing. Maybe I know that these should be marked as missing values. I could do that. And this would be a way, using this kind of functionality, you could write a function that's arbitrarily complex, makes a lot of decisions on individual values of a row, and the result of running that is you get a data frame that you can actually use for stuff. Does that kind of answer your question? Okay. That's the best way I found to do data cleaning with Pandas, is to write a function that for basically each column does something complicated with it that I know will get me the right answer, which some of it might be, okay, just throw this out because it's crap. Good question, thank you. So something else we can do with our data frame, we could actually change, we could actually, for example, delete columns. So for example, if I wanted to remove a column entirely from the data structure, I could call del. Del is a Python built-in. It basically means delete the name for something. So if you have a name, say a equals 2, and you say del a, what you're saying is take this name and forget it. It's gone. It's not in the Python session at all anymore. Remember, there's names and objects in Python. Del doesn't delete the object, it deletes the name that you specified. There may be more than one name pointing to an object. So in this case, I deleted the name A that pointed to 2. A little bit of a Python aside. If I have, say, the name A and the name B, and they both point to, say, this NumPy array, and what I call is del A, what I've done is I've gotten rid of that name, but there's still a name somewhere in my session that points to that NumPy array. So we can still get to it. If later on, or maybe somehow this name goes out of scope and no longer exists, or I call del B, there are now no longer any names pointing to this object. What that means is this object is fair game for garbage collection. Eventually, the Python interpreter will say, hey, nothing points to that anymore. I can just delete the underlying object that's in memory. And this gets important when you start loading big Pandas data frames into your computer's memory. Say you had lots of CSV files that were full of wine. We have one so far, but there's a second one in there. If you tried loading them all into data frames at once, perhaps it's actually too big for your computer's memory. It is useful sometimes to call del on the name that points to an object, because you'll delete the reference to it and make it available for garbage collection. Another way to make it available, instead of deleting the name A, so say we just decided not to do this, but instead pointed A to something else, like, okay, now A points to 2. So in that way, the reference doesn't point to the old data structure anymore. These are just things to keep in mind as you use Python, because they come down to how Python works. I was hoping somebody would ask that question. He asked, is there an explicit way to call the garbage collection mechanism? That is, if I have a Pandas data frame that's 5 gigs large in memory and my computer only has 8 gigs and it's grinding to a halt, how do I garbage collect? Well, you can do import gc and then call gc.collect, and that will immediately call the garbage collector, which will go looking for objects that have no references to them and just free the memory up. I have written code that does data analysis where I've done an explicit gc.collect in a loop there to make sure that it smacks that off. There's a cost to that though. There's a performance cost, right? If you're forcing the interpreter to delete stuff, whereas it really didn't need to, you're costing time, but saving memory. All right. It's also possible to slice our data frames. So we just did loc, where we selected a specific value, but we did see an example of slicing we sliced out a single row earlier, right? But we could slice, say, 5 to 10. This is labeled-based indexing, or label-based slicing. It turns out that if you were to do, let's see, for example, if we do describe, this gets us something similar to we saw with series.describe, except it gives us a big data frame full of descriptive statistics. For each column, it gives us the count, mean, standard deviation, min, all this stuff. You could actually slice this, or at least I'm going to find out if this will work as I expect it to. And that kind of looks like magic. Basically, we took this data frame that we generated by calling describe that had an index with a bunch of string labels on it, and you could actually slice that. You could say, go from mean to min, and because there's an order to these rows, it's actually pretty well defined what that means. It says go from that one to that one, including the last one. I think you could also put a skip here. Yeah, that'll work. So you could say, give me every other row that results from that. It's kind of a weird thing to do for this particular example, but it shows you kind of the flexibility of these structures. And if you only wanted at that point only chlorides, you could select that one out, right? Because what we got was a data frame, so you could do the same kind of operations that you previously did for these things. And if you wanted element 0, you could get that. Or you wanted the same thing, which would be element mean, you could select that guy out too. So you could string these operations together, kind of like we did for NumPy arrays. If you recall, on Saturday we wrote some functions where we just strung a bunch of methods together. So what I'd like you to do, we're going to do a little challenge exercise, is select the wines with, this is going to require you to do some playing around because I haven't explicitly shown you how to do some of this stuff yet. That's okay. Select the wines with volatile acidity less than 0.58 and obtain the mean density of these. Put your stickies down for me. When you've done this and you're satisfied with what you have, put that blue sticky up. If you'd like me to come by, go ahead and put that orange sticky up, and I'll be by shortly. Again, I said this one doesn't have, I haven't quite shown you all the pieces you need for this, but think back to what you did for NumPy and Boolean indexes. So we had an example at the beginning of class of creating a Boolean index. You can do something very similar with the Pandas data frame and the columns in it. Give yourself the freedom to play around.